Hi, today we're going to talk about limits at infinity and horizontal asymptotes. So first up, the limit as x goes to infinity of f of x, this describes how the graph behaves as x grows large. And similarly, if we look at the limit as x goes to negative infinity, that tells what the graph does as x grows large in the negative direction. And we can determine this from looking at the graph. So if, well, let's just look at a few examples here. This first one, if you look at it, as x grows large, if we trace along the graph, as x grows large, we're getting closer and closer to this line here. So as x goes to infinity, f of x here is going to 2. And similarly, if we go in the negative direction back here, as we travel along this line, the x or the y coordinate gets closer and closer to 2 as x goes toward negative infinity. So this is also going to be 2. And this graph we would say has a horizontal asymptote at 2, because right here I could draw in a line at 2 that'll pop into place. I can't quite get the line to look right, but anyway, there is a line here at 2, at y equals 2, that it approaches as x grows large. So we'd say this thing has a horizontal asymptote of y equals 2. Now this next example, if you look at it and trace along with what happens, as x grows large, this keeps growing up forever. So as x goes to infinity, this also goes to infinity. As x goes to negative infinity though, it's going down forever. So this is negative infinity, and this graph has no horizontal asymptote. In order to have a horizontal asymptote, one of those two limits has to be a finite number. Okay, this last example, this is it's a sine wave, and notice what happens when x grows large. It just keeps going back and forth, so it never approaches a particular number. So we'd say that this limit does not exist. And the exact same thing happens when you go toward negative infinity. So this also does not exist. And this graph also has no horizontal asymptote. So in all these cases, we're just looking on the graph at what happens when x grows large in one direction or the other. Let's look at this next example down here. This graph, if you wanted to actually get this graph, if you wanted to come up with it, it's sine x times a decaying exponential. So if you look at it, as x goes to positive infinity, notice over here as we start moving, the further out we go, it gets closer and closer to 0. So even though it crosses back and forth on here, we can go out farther and farther and get closer and closer to 0. So the limit as x goes to infinity of this is 0. Now I didn't write it on here, but if we put it in, the limit as x goes to negative infinity of this function, which I called s of x for some reason, as x goes to negative infinity, this just keeps going back that way. So it keeps going up and down. It never approaches any particular value. So this limit, I shouldn't say equals, let's just say the limit does not exist. So graphically, if you're looking for horizontal asymptotes, or if you're looking for limits at infinity or negative infinity, that's all you really have to do. Now, if you're asked to find some limits at infinity from an equation, then you need to know a little more about the behavior of the equations. First up, polynomials. Polynomials have no horizontal asymptotes, and their limits as at infinity and negative infinity are always going to be either positive or negative infinity, and that's going to depend on the leading term. instead of jumping into some examples, let's look at Desmos for a second. So for example, if I take this and graph a polynomial, let's just say x squared. If you look at this, for this one, if x goes to infinity or negative infinity, in both directions, it's going up. So this has no horizontal asymptote, and if you took the limit as x goes to infinity or negative infinity, it's going to be positive infinity. And if I change that infinity there to negative infinity, it's still true. Really, the only thing that matters for a polynomial here is the degree and also the sign. If I change this x squared to, say, x cubed, notice as we go toward positive infinity, the y-coordinate goes to infinity. I'll try to do that without scrolling too much. And if we go toward negative infinity, as x goes to negative infinity, y also goes to negative infinity. Let's put in a crazy polynomial. Negative 3x to the fifth minus 5x to the fourth plus 2x squared plus 1. All right, so we get this crazy looking thing. If you zoom in, it's got a lot of humps going on in the middle. But if we were to ask about this, I'm just going to call this g of x. And I'm not going to copy this one down. But if I come back up here and I'll look at this g of x, when x goes to infinity, all we have to do is come over here and look at what's happening. As x grows large, y is growing large, negative. You can see the graph, it's going down. So this is going to be negative infinity. And similarly, if we go, x is going to negative infinity of g of x, we get on the graph and we see what happens as x grows large in this direction. Well, as x grows large, y grows to positive infinity. So this is going to be positive infinity. The only thing that really matters there, though, are two things. This, the sign of the leading term. If I change this to an even number, notice they both go down. So on all the leading numbers, they go down. Or I'm sorry, on all the even numbers, both of these limits are negative infinity. If I put in an odd number, okay, if I put in an odd number, this one threw me for a second because it looks like both of them are going down, and that's true. But I've got this x to the third. X to the fourth there is now my leading term. So they're both going down. If I change this to, say, x to the fifth, notice we've got one going up and one going down. If I want to change it so that one goes down and one goes up, I could just change the sign of this. And we get this graph. All right, let's do a couple of examples. Let me switch back to this. So we've got a handful of examples here. On this one, we've got x squared. X goes to infinity of x squared plus 3x minus 1. Now, I could go over to Desmos and graph this if I wanted to. But actually, let's do that for this first one. If I put that in and say x squared plus 3x minus 1, you can see that it's as x goes to infinity, y is growing also to infinity. The truth is, the two terms, 3x minus 1, those don't matter. If I take those off and just leave that original term there, the original leading term is the only one that affects the end behavior. So it's the only one we have to look at to determine these limits. So if I look at this, I can just look at this and say, what happens to x squared when x grows to a large positive number? Well, if x grows to a large positive number, x squared is also going to be large and positive. So this limit is going to be infinity. All right, the next one. As x goes to negative infinity. Again, we only have to look at the leading term here. When x goes to negative infinity and we've got x to the fourth, think of that as being a negative large number raised to the fourth power. Well, you've got 4 of these multiplied together, so that's going to make it a positive large number. So this is going to be positive infinity. Now this next one here, the leading term is negative 3x squared. So as x goes to negative infinity, you have to think about what you've got here. We've got a large number cubed multiplied by 3. Actually, what I'm doing here is I'm thinking of the signs separate from the numbers. So I've got a negative, a 3, a negative cubed, and a large number cubed. So a large number cubed times 3 is going to be a large number, so that tells me it's infinity. And then if you count the number of negatives we've got multiplied together, we've got 1, 2, 3, 4. So an even number of negatives makes this positive. So this is going to be positive infinity. And if we wanted to double check this with Desmos, all we'd have to do is type it in. Let's see. Minus 3x to the third. And notice this already shows us that as x goes to negative infinity, our function grows to infinity. And if I put the other terms in, they're going to affect the shape a little bit. They're going to affect the shape of things, but it doesn't change the fact that this goes to positive infinity. So there's no need to look at anything but the leading term. All right, let's look at rational functions. Actually, I'm going to save rational functions for the next video.